Hello, I'm Ben Kaiser. I'm a PhD candidate at the University of North Carolina at Chapel Hill, and I'm a 2021-2022 NC Space Grant Graduate Research Fellow. We're talking about that research today, which focuses on ancient extrasolar planetesimals and what they can tell us about stuff in the galaxy. So some extrasolar planetary, some exoplanets come too close to their host star, and they're ripped apart by tidal forces. This material then flattens as it approaches the host star, forming a disk kind of like the rings of Saturn. And the host stars that I'm interested in are known as white dwarfs. And these are leftover remnants of stars, including those like our sun. And then when this exoplanetary material gets accreted by these white dwarfs, it gives us the chance to measure the composition of the exoplanet, basically. This is what my space grant research focused on. So we obtained new spectroscopy of 3 white dwarfs that are polluted with lithium bearing materials using the Goodman spectrograph on the 4.1 meter SOAR telescope. All of these dips in each spectrum or whatever, well, most of the dips, some of this is noise. Most of the dips are from metals, meaning astronomy metals, so everything heavier than helium. So like lithium, sodium, calcium. This squiggle is magnesium hydride, which is a new discovery by us for this object. We also got a better limit on potassium, and then we confirmed a bunch of metal lines previously published by other people, but progress nonetheless. There is a lot of lithium though, and the 5 white dwarfs that have lithium detections, 2 of them not being pictured there because we got spectroscopy years ago in our first paper we did on this. At the time of discovery, there were 2 explanations put forward. Well, each discovery paper put forward 1 explanation for why there's so much lithium. One explanation was old objects have less of everything else, which is what we said. Because lithium is made in the Big Bang, no other heavier elements are. So lithium to like calcium ratios will be higher than in the solar system at times way far in the past because there was less calcium, for example. The other explanation put forward by the second paper was that it is continental crust material, like the stuff under your feet right now, unless you're in the ocean for some reason. That material is higher in some alkalis and stuff like that. So to figure out which one is correct, or if either is, I decided to compare element by element using newly obtained values for several of the white dwarfs. Lithium, we can see that continental crusts could maybe explain 4 out of 5, but this one doesn't work for, which is really problematic for material being continental crust because you can't get up to here for continental crust. Other metals, ratios are, some of them are a wash. These ones are problematic for continental crust. Over here, the iron group, potassium, some of them support continental crust, some don't. It's not really clear. Also, as part of my space grant work, I obtained better total ages for the 5 lithium polluted white dwarfs. The one not pictured here is the JT24 green one, and it can't be because it is too low in mass to actually go through this process to get a total age, which is unfortunate. But yeah, so I implemented new model tables and atmosphere types. Huge improvements in my total system age estimation. Also diffusion timescales for those abundances back there. But putting those 2 things together, we can compare to the expectation of how lithium should have changed in time, which would be my hypothesis. And it doesn't perfectly work, which is probably partially a function of this predicted curve being from before there were lithium polluted white dwarf measurements, because they're new. They've existed, they've been published for only a little over a year now. And then our ages might still be problematic, which could be a result of masses or something. And so over time, we expect that we'll get better age determinations because we'll be able to account for different metallicities, because these things probably have low metallicities. Atmospheric modeling of white dwarfs should improve because there were dramatic improvements in that in the last 2 years, and that's going to keep getting better. And then we're going to find more lithium polluted white dwarfs, which will increase the sample size, making this not just 4 points on a plot. Thank you.